Brooklyn, what lesson number is this? It's because it's kind of a continuation of what we did, but if I tried to cram that all into one long lesson, it would have been overwhelming. Lesson 1.5, Trophic Pyramid Calculations. So there's something called, and you can underline this if you want to, the rule of tens. Marco, this is a rough average. The rule of tens in some situations, it's not a 10, it's a 20 or a 15 or a 6, but as a rough guess, as a rough average, we say this. In a food chain, energy is passed from one link from one trophic level to another. However, not all of the energy that is found at one level in one organism can be passed on to the next. Energy lost at each level can vary from 50 to 90%, but when calculating, we're going to base it on the rule of tens. We're going to assume that 10%, it's a rough estimate, but it's pretty good, that 10% of the energy available in an organism, when an organism dies or gets eaten, only about 10% of the energy that it contained gets passed on to the next level. So here's some really nice numbers. If we have 1,000,000 joules of sunlight, remember energy is measured in joules, the primary producers might only be able to absorb about 10,000 joules of that. They'll absorb 100,000, but they'll pass 10,000 on to the next level. The other 90,000 they use to grow themselves. Then the primary consumers, they only have about 10% of that energy to work with. So if we know how much energy is available at this level, and if we know, for example, Allie, how much energy a locust needs to survive, we can make a reasonable estimate as to what population of locusts this ecosystem can support. On the next level, the secondary consumers, you lose about 10% again. What's the easy way to calculate 10% in your head, by the way? What do? In fact, even if there's not a zero, just lop off the last digit. We're going to be fairly rough anyways, okay? So you probably don't need a calculator for that. Later on, you'll have to do a little bit of dividing, and that's where you might need your phone calculator for, okay? And at the very, very end, even though we started this ecosystem with 1,000,000 joules of sunlight, 1, 2, 3, only 4 pyramids, 4 trophic levels up, and we're down to 10 joules, which is why typically, you'll notice lots of herds of zebras. You don't see herds of lions. You see a few. Put your pencils down, look up. Percent rule. We can calculate the amount of energy available in each trophic level. And again, Brooklyn, a trophic level is when you move up the food chain, as it were. So we start with the producers. How many joules of energy in this food chain are available from the producers? Okay. The locusts are the primary consumer. How much energy will they have available if there's only 10% that gets passed on to them? A 4, a 5, and 3 zeros. That's how I do it, Jimmy, so I don't, because it's easy to miscount zeros, so a good way to do it, write down the non-zero digits and then just one fewer zero than you had before. So we would have 45,000 joules of energy at this level. How much am I going to have for the lizards, the secondary consumers that eat the primary consumers that eat the primary producers? Okay. How much energy is going to be available for the tertiary consumer, the snake? Yep. Don't put an extra zero there, Mr. Dewick. So, and I've just made these numbers up. I didn't look them up. I should have. Suppose an average snake needs 90 joules of energy each day to survive. Roughly, how many snakes can be supported in this food chain?
5.
How'd you get that?
450 divided by 90.
Now, this is a dramatic oversimplification page because, of course, in real life, there would be several hundred different producers and several hundred different primary consumers, and then fewer, but still a few hundred secondary and tertiary. So the webs get really, really complicated really fast. We use computer models to track it all. But this is the gist of how we roughly do population prediction in wildlife. Okay. I'm simplifying it, but it starts like this. All right, given the following, next page. Suppose the sun supplies that much energy, 990 million joules of energy. How much will be available for the osprey? So let's see. If we go right here, how much is available for the plants? Okay, so they're going to get all of it. How much are they going to pass on to the next level? How many zeros are there? 1, 2, 3, 4, 5, 6, 7 zeros. So the shrimp are going to get 9, 9 with 6 zeros. The minnows are going to get 9, 9 with 5 zeros. Are you seeing why I count zeros, Jimmy? It makes it way easier. The perch are going to get 9, 9 with 4 zeros. The pike are going to get 9, 9 with 3 zeros. And the osprey are going to get 9, 9 with 2 zeros. Then I go back and I put the commas in. So how much is available for osprey? I'm saying roughly 9,900 joules.
Do we lose marks if we don't put the joules?
In Physics 11 and Physics 12, I'm fussy about units. Here, I won't freak out. So if this was your ecosystem, and this is, again, Ali, a really simplified ecosystem with only one straight line. Of course, they're much more complex in real life. But if an osprey needs 1,650 joules to survive, how many ospreys can this support? And this is where if you need to use your phone calculator, you can. And then when you're done using your phone calculator, you'll put it face down again on your desk so that you're not looking at your screen. Is it 6?
5 or 6.
What, is it exactly 6?
Yeah.
Yeah? So I was making up nice numbers. All right, this is a little more realistic, but even still, this is really simplified. So suppose sunlight provides that much energy. Now, it's providing that energy, David, there, and there. So it's being split, and I can't even assume that it's being split evenly in 3 separate ways. It's possible that some of those primary producers are producing more of the energy than others, are supplying more of the energy on the next level than others, but it's being split. How much energy is available for a giraffe? Oh boy, that's a tough question. That's a tough question. We have to make some assumptions. So let's make some assumptions. Let's assume that the energy is split evenly. Now, if we were biologists doing research, probably we wouldn't, Sarah, have to make these assumptions. We would have a better idea of how efficient this bush is compared to the grass, compared to the tree. But okay, so how would you figure that out? I would imagine you can study. It's a good question. I think you would study and actually like break up branches and figure out how much carbon was stored on each branch. Now the giraffes eat the leaves. The branches generally don't get eaten, although thin twigs do get eaten as well. So you're figuring out pretty quickly. It's a complicated, even simple questions get really complicated in biology pretty quick. So can someone divide this by 3 on their calculator? Because we need to split it 3 ways. What'd you get, Leah?
506.
Read me the digits.
516,816.667.
So I'm going to go 516,817 if I round off properly. Okay. So, how much energy is available for the giraffe? Well, 10% of that. How do I find 10% of that? There's no zeros this time, but what did I say the really easy method is? Just chuck the last digit. So we're going to have 51681 joules. Now, you can argue, Nick, should I round that 1 off to a 1 or a 2? We're so rough with this 10%, I'm not even going to be that fussy. In fact, Halia, you may notice I should have gone 0.6 repeating because we've got an extra jewel kicking around. We're being so rough with this, I'm not going to be that fussy. We're just trying to get an idea. Yeah.
Where did the giraffe and the rhino split?
Ah. Would it be divided by 2? Ah, so now we're having to make other assumptions. You can see how complex this gets really quickly.
And
It's
it's kilojoules.
kilojoules, you're right. It's 1,000 joules. So divide that number by 2. Use your phone calculator or do it in your head. I can probably do it in my head. 50,000, 21,000, 21,500, no, 20,500, 20,800, 20,000, is it 20,840.5? Double check me. 25,000, 25,840.5. So 25,841-ish joules-ish. Now, are we being fairly rough? Are we doing approximate? So if you, yeah, I'll fix that in a second. Thank you, Nick. Candy for you. Look up, new symbol for you. If you're doing approximate instead of doing an equal sign, if you do a curvy equal sign like that in math, that means is approximately equal to, is roughly equal to, best guess going to be close to. So I'll probably do that because we're making rough guesses here. How much energy is available for a skunk?
Wouldn't it be 10% of 5.6?
Well, let's see. First of all, we have 10% mentioned right there, but then it splits up. We might have to assume in 2, and then we take 10% of what was left. 10%, and I'm not going to give you stuff that's tough in the homework, by the way. I just wanted to let you know we're real on the previous page, Amy. These are really simplified food webs and trophic level pyramids. They get tougher pretty quick. Okay, so if we wanted to walk through this, what would we do? We would start here with 516,817. We would.
Grasshopper, because we already know how much it is on the
That's
second
what we're
level.
doing.
Okay, so you're saying start there with the grasshopper.
Yeah, if we
Okay, and that would be that number. Knock off a 10.
it would be the 25.8.
It'd be the 25.8. Oh, you're saying since we split it already, the bird is going to have that much?
The bird will have 10% of that.
The bird will have 10% of that? Oh, because it's already being split here by the... Oh, gotcha. Okay. So, let's make a little note here. This is... so you're saying grasshopper is 25,841. And then we go bird. What's left for the bird? Split that. So divide by 2. 10% and divide by, I think it's 10%, but we're also dividing by 2, right? So it's going to be 2,584 divided by 2, which is about what? 84 divided by 2 is 42. 2,500 divided by 2 is 1,250. 1,292. Double check me. No, not 1,000. Did I say 900? 1,000. 1,292. Yeah, that's what I said. Yeah.
Wait, Mr. Dewey.
Yep.
In the beginning, the grass splits into 4.
Oh, the grass splits into 4.
Yeah.
Okay.
Oh.
Cross it out. So we should divide this by... So the grasshopper is going to have this number, and now I'm going to bring out the big guns, the big calculator. 516,817. It splits into 4. So you're saying, and then divide by 10. You're saying the grasshopper starts with that?
Yeah.
Say, so 12,920. And then the bird is going to be this number, 10% of it. divided by 2. So Jimmy, you can see there's the grass is getting split into 4. 1, 2, 3, 4. Okay. And then, so that gets us to the grasshopper. We split it in 2 to get to the bird. So 1292 divided by 2, and I get 646. What level is that? That's the bird? No, that's the... yeah, that's the bird still. Right? Now, skunk. 65? Sure. How much energy is available for a lion that eats a rhino? So you can see, I'm not going to give you any more of this stuff. In fact, we're not going to bother doing this. This is a little more convoluted than I planned. I'm going to be asking, though, I hope, Brooklyn, you can follow these ones here, the single chain ones. Okay, so I have some homework for you to practice. Oh, no, hang on, we got one more. Here's a nice straight one. So we're going to skip number 3. Sunlight gives the plant 54,000 kilojoules of energy. Fill in the energy at each trophic level. So we have 54,000 kilojoules. Knock off a 0. Knock off a 0. Knock off a 0. How do I knock off a 0 from 54? 5.4? Sure. Okay. So let's write it down. Grasshopper was 5,400 kilojoules. Bird was 540 kilojoules. Snake was 54 kilojoules. What was that mentioned? Bird looks pretty cool or funny? Cool? Okay. So, how many owls can this food chain support? Could it support 3? Not healthily. In fact, as soon as you had 3, now you would have serious competition. Now they'd be competing for the same prey. Yeah.
Owls would be kilojoules, right?
Oh, thank you. You guys are catching me on the units. Pause for a second. Take a look at the homework. It's not very much, because I think you will need a bit of practice to get the hang of this. Also, I'm not going to be putting ecology on your final exam. I think it's important because we're going to be spending a couple of days talking about climate science, and there's lots of misinformation out there about it, but I'm not going to be assessing you on it or giving you a test or a final exam. You're just going to be doing homework. So if you take a look at the homework, what is a trophic level? I've given you definitions in your notes, or remember I also gave you an ecology mini textbook that has the definitions in it. What do energy pyramids represent? Explain how energy limits the number of trophic levels in a food web. Number 4. Then, if you want to take a look at the second page, so you're going to place these 4 objects in their appropriate trophic level in this food pyramid. Place these 4 objects in their appropriate level in the food pyramid. And this one here. And can you all look at number 6 for a second, please? Number 6. I did A for you. I'm giving you some numbers, and what you're going to do is try and calculate approximately what population could survive at each trophic level. So, for example, I started with 17,500 kilojoules of supply from the grass. 1,750 kilojoules got passed to the next level, and since grasshoppers only needed 0.5, you would have around 3,500 grasshoppers that are able to survive in this ecosystem. So calculate what population would survive at each successive trophic level. So I did an example for you. On the back page, you can try B and you can try C. And then answer for part D, based on your calculations in part C, can a lion survive by only preying on zebra, or will it need another secondary food source to survive? And we can all do number 7. An easy way to calculate how much energy is available at the next trophic level is to what? Okay, so you can write, use the 10% rule, or you can just even say, drop the final digit, divide by 10, or whatever. Okay.